Hello everybody, I am Dr. Punyadarshini Poonam Tripathi from Agricultural and Food Engineering Department, IIT Kharagpur. Today we will be discussing about the technological advancements in food freezing. Some book references along with journal and web references are listed here. Now coming to the food freezing, we all know that freezing is a very important unit operation in food processing, in which the temperature of food is reduced below its freezing point and a portion of the water undergoes a change in state to form ice crystals. So, due to the lowering of the temperature of the food, the water activity of the food reduces, and due to the lesser availability of water in the food material, some of the deteriorative reactions are also reduced. And this process has been proven to be very effective for reduction of microbial growth as well as to reduce the enzymatic activity. So, the typical signs of freezing involves the removal of both latent and sensible heat from the food product, resulting in the formation of ice crystals inside the food material. Now, coming to the different types of freezing systems. So, they are broadly classified as indirect contact systems and direct contact systems. As the name suggests, indirect contact systems, indirect freezers, they basically include the freezing systems that has a barrier layer between the food material and the refrigerant, and this barrier layer basically is the food package. So, the food materials are suitably packaged and accordingly it acts as the barrier layer between the food and the refrigerant. And the different types of indirect systems are plate freezers, air blast freezers and scraped surface freezers. Coming to the direct contact systems or the direct contact freezers, they are the freezing systems in which food has direct contact with the refrigerant, and the refrigerant basically can be high velocity cold air or some phase changing refrigerants. And the type of direct freezers includes fluidized bed, air blast freezers and immersion freezers. Now, coming into the details of these indirect contact freezers, we can see first one is the plate freezers. So, a schematic sketch of the plate freezer is shown over here. As can be seen, the product that has to be frozen is held between the plates. So, the barrier are the plates and the packaging material. Barrier to food is the plates and the packaging material. So, the package should be in the form of a parallelopoid or in the form of a rectangular shape, so that uniform pressure can be given from both sides. Two plates, we have two parallel plates in between which a food package has to be kept and uniform pressure has to be provided so as to freeze the food material. So, here heat transfer can be enhanced by applying pressure to the plates. So, both batch and continuous systems are available. So, this type of plate freezers are mostly suitable for fish fingers, hamburgers and products which are having rectangular shaped packages. Coming to the air blast freezers, here also we can see that this type of system is mostly suitable for irregular shaped food products. So, the food package again acts as the barrier film. Mostly the air blast freezers are continuous in operation, and freezing time here can be altered by changing the air velocity, length and speed of the conveyor. The third type of indirect freezer is the scraped surface freezer, and this system is mostly suitable for products like ice cream and margarine, where uniform product with smooth texture and consistency is the desirability. And this desirable texture can be achieved by controlling the crystal growth by using the scraper blades. So, here the crystal growth can be controlled by scraping the newly formed solid crystals from the refrigerated internal surface with the help of the scraper blade. Now, coming to the direct contact freezers, where we have discussed about this fluidized bed air blast freezers. So, this fluidized bed freezers utilizes the air blast with provision of partially suspending the particles. So, a photograph of fluidized bed freezer is shown over here. So, based on the fluidization technology, this utilizes the air blast where the particles or the food materials are suspended in the air stream, and as the particles were fluidized, maximum heat transfer takes place and quick freezing can be achieved. But here the only limitation is the size and the geometry of the particle. Immersion freezers are another kind of direct contact freezers, where the freezing can be achieved by immersing the food materials in the liquid refrigerant. As the product passes through a pool of liquid refrigerant, the refrigerant absorbs heat and gets converted to vapor form. Most of the system uses liquid nitrogen or carbon dioxide as the refrigerant in case of immersion freezers. So, here is a pool of liquid refrigerant where product is entering into it, getting suitably frozen, and these frozen products can be liberated out. The fundamental of freezing lies in the freezing curves. As can be seen, the freezing curve of pure water and food product is shown over here. So, the freezing point temperature for water is 0 degree centigrade. So, if we begin with water at a higher temperature, initially a temperature drop below 0 degree centigrade occurs. This means that there will be subcooling. Later, due to the beginning of the ice formation, fusion heat will be released and the temperature again rises to 0 degree centigrade, and at this condition the most of the liquid part is converted to ice and the temperature remains at 0 degree centigrade. So, when the, as we can see, so after subcooling, due to beginning of ice formation, latent heat of fusion is liberated or released and the temperature rises to 0 degree centigrade and remains as it is, and afterwards again once all of the water changes to ice, the temperature gradually drops, that is temperature reduction takes place up to the storage temperature. Now, coming to the freezing curve of the food materials. So, various stages of food freezing can be explained here. So, the freezing curve of food material varies or deviates as compared to the freezing curve of pure water. So, here again if we start with food product having temperature higher than the freezing temperature, then temperature drop takes place below the freezing temperature, that is A B basically represents the removal of sensible heat with no water to ice transformation. Now, following the onset of B, the latent heat of crystallization is released, which aids in increasing the temperature of the product. So, C basically represents the initial freezing point where ice formation begins. Now, between C to D, the major portion of the water crystallizes, and E is basically known as the thermal arrest time, but before E, this point D is designated as the eutectic point. Now, from E to F, if we can see, F is the completion of the crystallization process. Now, point E or the thermal arrest time is responsible for two distinct freezing processes. One is slow freezing, when the thermal arrest time is greater than 30 minutes. Similarly, fast freezing, when thermal arrest time is less than 30 minutes. So, during the freezing process, the very important aspect is to calculate the heat load or the total enthalpy change during the freezing process, and this is required for suitable design of the freezers as well as uniform refrigeration circuits. So, the total enthalpy change delta H can be designated as the summation of two sensible heat components and the latent heat component. So, delta H is CPU into Ti minus Tf. CPU is the specific heat capacity of the unfrozen food. from initial temperature to the freezing temperature plus latent heat of fusion, that is the latent heat part, again from the freezing temperature to the final storage temperature, this is the sensible heat part, that is CPF, specific heat capacity of the frozen food, into freezing temperature minus the final or the frozen temperature at the storage condition, where Ti, Tf and T final are the initial, freezing and the final temperatures. CPU and CPF are the heat capacities of the unfrozen and the frozen food materials, and lambda is the latent heat of fusion. So, in freezing process, the freezing time plays a very important role, because suitable freezing time decides the final quality of the frozen product. So, time of freezing is a very important parameter in order to design the freezers and optimizing the freezing characteristics for different kind of food materials. So, there are basically two methods are normal in practice which predicts the time of freezing. First one is the Planck's equation, second one is the Nagaoka's equation. Planck's equation is less cumbersome, but has certain limitations. And the second method, that is from Nagaoka equation, it basically depends on the physical properties of the process as well as the food materials also. So, we will be discussing both the methods. So, coming to the Planck's equation is the very popularized method for estimating the freezing time, and that is being proposed by Planck in 1913 and was later applied to the food by Ede in 1949. But this method takes into consideration a number of assumptions. First assumption is initially the whole food is at a distinct freezing point. That means the freezing point for the frozen and the unfrozen layers are same. Thermal conductivity of the food is constant and the frozen and unfrozen layers have equal density. There is a distinct interface or ice front which moves from the freezing medium into the food block at a uniform rate. Heat capacity of the frozen layer is negligible and heat transfer is sufficiently slow that it approximates to a steady state process. So, under this list of assumptions, Planck's equation has been derived, but this is the first equation or the first freezing time calculation based on Planck's equation, and based on this Planck's equation other modifications are being attempted by different researchers, and that is coming into picture. Now, according to Planck's equation, this is a Planck's model where a food block having cross sectional area a meter square is being shown over here, and it has a thickness of, the food block has a thickness of A. Now, the surface temperature of the food on both sides of the block is represented as Ts, and Ta is the cold air temperature. Freezing takes place from both sides of the block. So, we have frozen layer on both sides having thickness x, whereas the unfrozen layer is present at the center, as can be shown over here. So, Tf designates the initial freezing point temperature, Ta is the temperature of the surrounding air which is normally the cold air, Ts is the food surface temperature, x is the thickness of the frozen layer, lambda is the latent heat of fusion, and rate of heat transfer we are designating as Q. Convective heat transfer coefficient is watt per meter square degree C, and Kf is the thermal conductivity of frozen layer, and rho f is designated as the density of the frozen material. So, in order to derive this time of freezing process, so we should consider the rate of heat transfer from the surface of the block to the surrounding air, because initially the cold air has a lower temperature as compared to the temperature of the food block. So, there will be heat transfer, basically convective heat transfer from the food surface to the surrounding air. So, this rate of heat transfer can be designated as Q, that is H A Ts minus Ta, where Ts already we have shown as surface temperature of the food and Ta is the cold air temperature. The rate of heat transfer through the frozen layer is governed by Fourier's law of heat conduction, and according to Fourier's law of heat conduction we can write Q is nothing but equal to Kf thermal conductivity of the frozen layer into A Tf minus Ts upon x. So, this freezing process will continue unless and until this thickness x will be equal to A by 2. That means, both the frozen layer will come to the center, so that the whole food block will be frozen. So, in that case this x is nothing but equal to will be A by 2. So, this is the condition when we can say that the freezing process is complete. Now, the rate of removal of latent heat of fusion is given as Q is nothing but equal to rho f, A lambda is the latent heat of fusion, and this frozen layer this moves with certain velocity into the center of the food block, that is at a velocity of dx by dt. Now, this surface temperature of the food material has practically no significance. So, in this regard, because that is not known in the initial condition. So, we can eliminate this Ts from both the equations, equation 1 and equation 2, and we arrive at the expression Q upon Ha plus Ta is nothing but equal to Tf minus Qx by Kfa. And if we rearrange this, we can find this expression Q in terms of cross sectional area of the food block into Tf minus Ta upon 1 upon H plus x by Kf, where H is the convective heat transfer coefficient and Kf is the thermal conductivity. The rate of removal of latent heat from the unfrozen layer must be equal to the rate at which heat is transferred through the frozen layer to the surrounding air, because this is the condition when we can say that the freezing process is continuing. That means, the rate of removal of latent heat from the unfrozen layer must be equal to the rate at which heat is transferred through the frozen layer, both should be equalized. So, once we do that and again we rearrange the equations and integrate it with proper limits. So, we can get dt from this previous equation, we rearrange it and we got this equation and we integrate it with proper limits from time t is equal to 0 to total time t, and this is at 0 to A by 2. What is A by 2? Already I have shown here. So, suppose we start from here. So, our distance x is 0 here, and when we reach at the center, so x is nothing but equal to A by 2. So, this is the condition at which we can integrate the same time as well as the distance through the food block. So, here by solving this equation we are getting the freezing time, which can be represented as rho f lambda upon Tf minus Ta into A by 2h plus A square by 8 Kf. However, the generalized form of this equation can be written in terms of the geometrical constants, that is Pa by h plus R A square by Kf, because this part remains the same as it is. So, this P and R, these are the geometrical constants and they take the values for different regular shaped geometries. For example, for an infinite slab, the value of P can be considered as 1 by 2 and R as 1 by 8, where A is the thickness of the food product. Similarly, for the infinite cylinder, the value of P is 1 by 4 and R is 1 by 16 and A represents the diameter of the cylinder. And similarly, for a sphere, the value is 1 by 6 for the constant P and 1 by 24 for this geometrical constant R, and A represents the diameter of the sphere. So, by assuming these geometrical parameters, we can put over the Planck's equation to get the freezing time. So, there are certain limitations of the Planck's equation, as it lacks accurate physical property data. The latent heat of fusion here is usually assumed to be the product of moisture content and the latent heat of water. It takes no account of sensible heat changes and therefore not suitable for predicting the total processing time. In Planck's equation, sensible heat part is not coming into consideration. So, it cannot predict the accurate processing time. In this regard, one scientist Nagaoka, he has considered certain modifications over Planck's equation and developed an expression to calculate the freezing time more accurately. So, Nagaoka's model takes into account the time required to reduce the temperature from an initial temperature Ti, that is above the freezing point temperature. This is first aspect, because for sensible heat change we need to consider the initial temperature of the food product to the freezing point temperature, and that part has been taken care by the Nagaoka's model. So, there is temperature reduction from initial temperature Ti to the freezing point temperature Tf. It contains an empirical correction factor. Nagaoka's model considers an empirical correction factor and also introduces the latent heat of fusion in equation 8. Equation 8 is already the Planck's equation. In the same equation, Nagaoka has done the modification in terms of incorporating a correction factor and introduced the latent heat of fusion. This latent heat of fusion in equation 8 has been replaced. Latent heat of fusion is considered by Planck's equation, but in Nagaoka equation this latent heat of fusion alone is being replaced by the total enthalpy change during the process, that is delta H, that is the total heat load. So, freezing time is corrected in the form delta H, that is the total enthalpy change during the process, which considers both sensible and latent heat part, into density of the food material divided by Tf minus Ta into, this is the correction factor, 1 plus 0.008 into initial temperature minus freezing temperature into this geometrical parameters remains the same, Pa upon H plus Ra square by Kf. Now, based on this Nagaoka's equation, we can solve one problem here. A factory produces burgers at the rate of 5 tons per day and works for 2 8-hour shifts. The burgers enter a high velocity blast freezer at a temperature of 18 degree centigrade and frozen down to minus 15 degree centigrade. The following physical property data are given. Freezing temperature is minus 2 degree centigrade, that is Tf is given. Frozen density rho f is given. Thermal conductivity of the frozen food Kf is given. Heat capacity of unfrozen food Cpu is given. Cpf is also given and latent heat of fusion is given. We have to calculate the necessary heat removal during the production process. What is the necessary rate of heat removal during the production process? And if the burgers of 20 millimeter thick are to be frozen using air at minus 32 degree centigrade, then we have to find out the freezing time, provided the heat transfer coefficient is given as 200 watt per meter square Kelvin. Now, coming to the solution part, first we have to find out the total heat load per unit mass, that is given as delta H. So, if we put the respective values, everything is given in the problem. So, we can find out the delta H to be 273.5 kilojoule per kg. Now, the mass has to be removed from 5000 kg over a 2 8-hour shift, means 16-hour period, and therefore, the rate of heat removal is designated as Q, that is 5000 upon 16 into 3600, because we have to convert it in terms of kilowatt. So, we got Q as 23.7 kilowatt. Using Nagaoka's equation, if we put the respective parameters, then we can get the freezing time to be as 960 seconds. Now, coming to some advanced methods in the food freezing. So, here we can see there are some advanced technologies for achieving faster freezing rate, which employs ultrasonic assisted food freezing, high pressure freezing, and there are certain procedures for controlling the freezing process with antifreeze proteins. Now, in ultrasonic assisted food freezing, basically ultrasound is applied just to the phase change stage. During the phase change stage, the ultrasound has to be employed in order to induce the nucleation process and to promote the subsequent ice crystal growth. So, there are mainly two aspects of power ultrasound initiated nucleation process. First one is the primary nucleation and second one is the secondary nucleation. So, primary nucleation occurs and in which the cavitation effect results, that is basically cavitation effect resulting from the power ultrasound can generate a large number of cavitation bubbles, which can act as the nuclei for crystal generation and followed by nucleation. Similarly, in secondary nucleation, the power ultrasound can break up the big pre-existing ice dendrite crystals into smaller fragments. The violent agitation that is generated from ultrasonic microstreaming is basically responsible for enhancing the heat and mass transfer phenomenon during the freezing process. So, ultrasound or ultrasonic application during freezing is mostly employed during the phase change condition. Next technique of freezing is the high pressure freezing. So, here the phase change temperature of water basically decreases with pressures from 0 degree centigrade at 0.1 megapascal to minus 21 degree centigrade at 210 megapascal, and the opposite effect is observed above this pressure level. This phenomenon basically allows to carry out different high pressure processes of freezing and thawing of food materials also. So, most important high pressure freezing is the pressure shift freezing. This is very important. Here basically the food is kept in an high pressure vessel and the temperature of the chamber is maintained above the initial freezing temperature of the food material. The vessel is basically closed and the pressure increased up to a certain limit, so that the freezing is not feasible. So, holding pressure and temperature at these conditions for the desired time causes drop in the food temperature until it equilibrates with the media. So, during the pressure release stage, sudden depressurization causes depression in food temperature, and after a while when sufficient pressure difference is reached, nucleation begins to start. Subsequently, temperature increases up to atmospheric freezing temperature, promoting ice crystal growth, and homogeneous nucleation occurs continuously with formation of smaller ice crystals. So, this is the basic mechanism of the high pressure freezing. Next, coming to very important aspect of controlling the freezing process with anti-freezing proteins. Anti-freezing proteins are the curious group of proteins that are produced by many cold climate organisms and are being explored in the food industries for enhancing the quality and nutritional value of food stored in cold storages. Anti-freezing proteins act by binding to the surface of the ice crystals, inhibiting the crystal growth by increasing the local surface area of the ice crystals. Anti-freezing proteins are extracted from various sources such as bacteria, fish, insects and plants, and used accordingly for various purposes also. They have the ability to inhibit recrystallization in food, resulting in reduced cellular damage in meats and to inhibit the appearance of ice crystals in frozen products. Ice growth inhibition is very important advantage of the antifreeze proteins, so that the food can be stored at supercooled states for a longer period. Antifreezing proteins act extracellularly and through direct mechanical methods also are found to be best suitable for introducing these antifreezing proteins in food applications. So, these are some of the advanced technologies employed in the food freezing sector. However, these processes are not yet commercialized and a lot more investigations needs to be done in order to got proper recognition in the food industries. Thank you.